$80 to $100. Shipped to you. Parts Depot is like the greatest ever.
Is that shipping in everything included, or is that just
It depends on when you get it, because a lot of the times they have deals for free shipping on all orders. Mine, I spent $132 on a tie rod end, and it was shipped to me within 2 days for free. Yeah, I would compare prices, but I'll get it from the dealer. We starting?
Yep.
All right.
DC circuit analysis, LC 138, and I'm just going to take the roll really quick for 28th. Corey Adams.
Here.
Can you just show me your notes in your notebook? Oh, you didn't bring a book today? Benjamin. Benjamin's not here today. Dakota.
Here, but one
No
here
notebook.
for the notes.
Jesse.
Here.
No notes. Christopher.
I think he's in the bathroom.
Oh, he's in the bathroom. Frederick. Oh, there you go. Wow, look at those notes. Awesome. Cool.
There's Bruce.
Christy, do you have any notes to show me for the last reading
Oh,
assignment?
yeah. I just got a call from my wife, so I won't have to leave early.
Oh, okay. Robert Lambert. What's that?
No notes.
Okay, I can't even see him. Gary, you have any notes? No. Don,
Surprise.
you have notes?
Yeah, I got notes.
Okay.
From here through here, all the way up here.
Thank you. That's good. Okay, good. Starting to take notes. Good. All great men, all great scientists always had notebooks. That's all I have to say. But they left. Albert Einstein, Thomas Edison, Alexander Graham Bell, anybody that was anybody left a notebook. I'm just saying. Clarence. I've got a notebook.
Starts here.
Yeah. Okay, thanks. I've got a continuous notebook for the last 11 years of. I buy really nice bound notebooks, and I have a complete work of almost everything I did in industry, so I can always refer back to it anytime I want. But okay. One comment is that we're going to have a rocket team meeting on Friday down the hall in the CAD lab, and it's going to be at 9. But he said that he would he would have another meeting for us at 9:50 after we let out of the digital class, because we have like that 30-minute break there. So anybody interested? We're recruiting. What's that?
What day?
Friday. This Friday.
How much does it involve as far as after school and weekends and stuff like that?
As much as you want to put into it.
Yeah, it's voluntary. Whatever you show up, you show up. You can't.
You'll be asked to do things, and you'll be asked to volunteer to do things, and whatever you want to volunteer or however you want to help. It's kind of a voluntary-based service, and but it's something that can go on your resume. I mean, this is voluntary, but it has shown to get some people some really good jobs, because it's something that goes on your resume, and it's something that industry partners and the local industry, they'd love to see it on your resume.
And anytime you can get hands-on, it makes it much easier to apply what you're doing.
Because it's highly promoted at the school. You actually have a final product that you can take pictures of and show people, and they can see it. And those guys, they come through here and we show it to them, and they say, "Who worked on this?" So you have something tangible. You don't just have, "Oh, I've taken, I've did some homework problems. I've been back on the bench and I've, messed around with a few wires and things like that." You actually have a final product that works. So.
Okay, I'll be there. Friday in between class?
Yeah.
I'll be there.
And today we also have a lab that's going to go along with the lecture today. So I would say for today, especially, I would take notes because the lab is going to be directly related to these notes, and you're not going to be able to do the lab if you can't remember the specific details about the lecture notes for today. You may have problems doing the lab.
It's also going to be on Moodle later on.
Yeah,
Okay, good.
I think they already are. So we'll go ahead and get started. We have a lot to cover. So today's lecture is entitled Passive Components, probably part 1, because we're going to continue this on Friday, or finish it up on Friday. So we've talked a lot about the basic physics and chemistry, that is, the physics being static electricity, current electricity, batteries, which is more chemistry. All these topics used to be considered electricity. Now they're considered electricity and magnetism in physics. They've kind of been removed out of the electronics arena, which is kind of sad. But now we're getting into the electrical circuits, which is more of a traditional beginning class in circuit design. So the basic concepts of electric circuits is that we have electrical current that will flow through a battery, just like we talked about how a battery works with a zinc and a copper plate. We have a continuous flow of electrons, but in order to have that continuous flow of electrons, we have to have a complete circuit with which the electrons flow. And inside the battery, there's chemical action going on that when the electrons are depleted, it creates more electrons. So it's a continual flow of those electrons are always supplied, as long as the battery is still good. But there's no chemical action or nothing happening until the complete circuit has been formed. In this case, the circuit is formed through the filament in the bulb, and then it returns to the positive terminal. This is called electron flow, the way that it's drawn here. We typically use conventional current flow. We would say that current or conventional current flows from the plus terminal through the bulb and to the minus terminal. We can also add an arbitrary ground signal here and say this is our reference ground if we wanted to have a standard positive volt system. Or we could ground the plus terminal. It doesn't really matter. The ground is just a reference terminal. We would call the lamp the load in this case because it's performing the work of lighting up the room and heating up. The load could be anything. It could be a motor, heating element, electromagnet, etc. Now, if we want to do more work, do something more useful, for example, if we had some street lights, some of the very first street lights were in series. Today, everything is in parallel, but you could potentially string some lights in series, and then the current would be forced to flow through each lamp, and the total amount of current through each lamp and through the entire circuit would be the same. And the total current would depend on the resistance of the lamps added together. So you'd have lamp 1, 2, and 3, and whatever resistance those had, if they had 50 ohms each, then you would have 150 ohms. So you'd have a reduced current through this circuit as compared to the first circuit. But really, right now, what we're trying to talk about is not Ohm's law and the resistance, but more of what does a series circuit look like and how can you create one. And what is the effect? Well, the effect of a series circuit normally is a reduced in current as compared to a simple circuit. So if you have one load element, if you put those loads in series, you're always going to wind up with a reduced amount of current through the series circuit with multiple elements as opposed to a single load. For a parallel circuit, you can see that the load goes directly across the battery. So in both of these cases, in all three of these cases, the lamp is connected directly across the battery. And so the same current that flows in the first circuit, which is the larger current, is going to be the same current that flows through each individual lamp. So you're not going to have a reduction in current through each lamp. Each lamp is going to operate as if it would if you just had one lamp connected to a battery, as far as the brightness, the heat, and everything generated from that lamp. Okay. So the only difference is you're going to have three of these currents is going to be flowing through this part of the wire, and then the current is going to split up here and then flow. So you have less current flowing through this wire than through this wire. Obviously, because you have to get all the current for this lamp through this main wire. And then we have a series parallel, so we have combinations of series and parallel circuits. For example, this is a combination circuit where you have a series circuit and then you have a parallel. So all the current that flows through the parallel lamps, they have to first go through these first two series circuits. So that is going to create a reduction in current in the two parallel lamps as compared to the pure parallel circuit. Now, since we talked about the lamp circuit, the parallel series circuit, now we want to talk about the symbols for those components, because we typically are not able to draw something so nice as this author who wrote this book, Forrest M. Mims III. So typically we use symbols that are a lot easier to draw. Okay, so for a battery, we typically use a long bar, a small, or a long bar, a short bar, and then that represents one cell. And so this battery, a battery means more than one. So this battery has two cells in it. So if the cells happen to be a 1.5 volt cell, then this would be a 6 volt battery. So each, for example, a car battery, lead acid battery would have a 2.1 volt cell voltage. So if you stack two of them together, then that would give you 4.2. Now, the correct way to do, for example, a car battery, a 6-cell battery, would be you would draw 6 of these large slash, small slash. You would draw 6 of those in series. But throughout history, throughout time, we have simplified the symbol for a battery just to normally just include 2 of those. Okay, and then we can put the voltage between the plus and the minus sign as a simple way to, as an abbreviated way, as a smaller way to save space, so we don't take up so much space. For a lamp, we typically just draw a line coming in, a loop, some type of a loop. You can get fancy or not, and then with a circle around it. And then, of course, we would just draw straight lines for the wires. And when we have a connection point of more than one point, so in this case we have 3 different wires that are connected, so in that case we would draw a circle to indicate there's a connection. Now it gets confusing when you draw a wire over a wire with no connection point, because the question is that a connection or not? So we want to always put a dot to make sure that we have that we show that we're having a connection. Okay, so let's talk about what is an electrical short. Probably a lot of people have heard of the term short. Short circuit occurs when a wire or other conductor is placed across the connections of a component. Okay, some or all of the current in the circuit may take a shortcut. The short circuits such as these are usually undesirable at best, and they can cause your batteries to discharge. It can damage the wires. It can cause the wires to melt, to ignite, melt, bad things. The reason for that is, let's say that we have a short somehow occur across this battery. Well, all the current, the battery is going to, after the electrons are removed from the copper or whatever lead, whatever electrode that you're talking about, the chemical action is going to continuously produce more. And so you're going to have a lot of current. In fact, the current's going to be determined by Ohm's law, which says I equals V over R. And if R is very small, you can use your calculator to show that if you have a very small number with a large voltage, V divided by a very small number, then you're going to get a very large current, thousands of amps. And so that amount of electrons pushing through a wire causes a lot of resistance because it hits the molecules, and the faster those move, then it starts creating random vibrations, which causes heat, and that heat is what causes the insulation to melt, and can actually cause the wire to melt as well. Okay, so we really want to eliminate those short circuits and make sure that we don't have those. And back in the lab, that's how we use the power supplies. We used to use the current limit. Those power supplies are current limited to 2 amps, so they're safe to use. Whereas some other batteries in your car would not be. There's the safety mechanism that they use in a car or a house would be a fuse. So where they would put the fuse as close to the battery as possible. The fuse becomes ineffective if the fuse is over here in another part of the circuit and you short the battery over here. The fuse is not helpful. So usually they make the fuses in a fuse box right as close to the battery as possible, or before it gets distributed to any of the other components, to protect against short circuits. And this is a caution that the human body conducts, and that you can normally about 40 to 50 volts is considered high voltage to start to shock you, but depends on if you're wet, depends on your body. Different people have different resistances, so you may be shocked at a lower or slightly higher voltage than 50 volts, depending on the situation, how well you're grounded and things like that. The next basic concept we're going to talk about in this series of basic electronics is electrical ground. One of the wires of an AC line is connected to earth by a metal rod. The metal enclosures of electrically powered devices are connected to this ground wire. This prevents a shock hazard should a non-grounded wire be made to contact with the metal enclosure. Without the ground connection, a person touching the device while standing on the ground or a wet floor might receive a dangerous shock. So, in a building, in this building, everything is grounded to rods that are driven into the ground a certain distance. I can't remember, 6 feet or 8 feet. 8 feet. Okay.
2 rods.
Okay.
Now.
Yeah, I used to know, but it was a long time ago. Yeah, those things are dug into the ground, and the idea is to get down to the water line so that you have good conductivity to the earth, and it makes sure that you have equal potential, because different places on the earth have different potential, so you want to make sure that locally you are grounded with whatever your local potential is. Okay.
They'll let you dig a trench and lay it in the ground instead of driving it in the ground.
Yeah. Okay. Ground also refers to the point in a circuit that is 0 voltage, whether or not it's connected to ground. So we've kind of tainted the idea of ground a little bit, because in an electrical circuit that's not connected to ground at all, for example, with a battery with your cell phone, we will refer to a certain node, common node in the system, as ground, even though it's technically not ground. But it really, we're just calling it a reference point. And they do have different symbols. There is an earth ground symbol that we can use. Okay, for example, we have this type of a ground symbol. We have
Is that earth ground?
that's chassis ground a lot of times. And of course we have this symbol for ground. This symbol for ground is trying to represent the earth, because really what it's trying to show you is that this is the earth. It's kind of trying to draw, this is the ground is what it's trying to show you. This is the earth. But the symbol looks like that. You have it's kind of a triangular shape. And then we also have a signal ground that we use in electronics that looks like that. And this refers to an analog signal ground. Okay? So these are the three grounds that we're going to use. Let me get rid of this one. Yeah. And chassis ground just means that you have a metal chassis that you're interested in grounding to prevent shocks. So this chassis ground. For example, let's say that we have two batteries here, and we connect these two batteries together here. Now, if we say that this is ground, then this terminal of the battery would be considered plus 1.5 volts or 1.5 volts. This side would be considered minus 1.5, because we've referenced in the middle. Now, conversely, if we connect this side to ground, to what we call ground, then we would say that this has 1.5 volts and this has 3 volts. Okay? Is that clear as mud, or is it clear as water? So depending on where you define your ground to be, makes a big difference on what we say the voltage is. Just to confuse you even more, okay, let's say that we say that this is ground. We just define this as ground. We'll scratch that out. If this is ground, then what you have here is 1.5. This is minus, and then this will be minus 3 volts. Okay, because now we've grounded the positive terminal, and so we get a minus 3 volts here. Okay. So it is important where you reference your ground, and where you reference your ground depends on what your rail voltage is. These are called your rail voltages, or because they represent the highest and the lowest voltage that you can attain in a system. Okay.
So rail voltage is the highest or the lowest voltage you're going to
Yeah. So this is your positive rail, this is your negative rail, we call it. Positive rail, negative rail. Okay, let's talk a little bit about pulses, waves, signals, and noise. Of course, electronics is the study of electrons and the behavior and their effects. The simplest applications is a DC circuit used to power lamps, electromagnetics, motors, solenoids. For example, let's say that we have a simple circuit here like the one that we showed before, except we add a switch. A switch could be simply a piece of wood with a couple of screws in it, aluminum, and you could just touch that, and that's a switch. Now when you touch this aluminum to this screw head that's connected through this copper wire, then it's going to make make the circuit.
Right.
And when you lift up your finger here, and it's going to break the circuit. Okay, so we call it make and break the circuit. Now, when this aluminum is pushed down, the light's going to glow. Of course, is when the aluminum is lifted up, the lamp is not going to glow anymore. You could use this simple circuit, for example, to send a Morse code signal across the country. This was the original Morse code, except you replaced the lamp with a solenoid or with a relay. Really was Morse code's invention, was using a relay. Yeah.
The
Yeah.
way the battery is hooked up positive to the side of the...
Yeah, normally this is considered ground, but it's not going to,
Yes.
it doesn't matter.
Okay.
There's no polarity on a lamp.
Right.
This simple circuit is really more useful than you might think, like you said, to send information. And of course, on, off. This is represents like a Morse code pattern and flashes and things like that. We'll get into more communications, and we have a class that specifically denoted for communications, and then in digital, we use these sort of waveforms in the digital design class. And when we start talking about these signals where you turn a signal on and off, of course, you get into wanting to look at these on an oscilloscope and looking at the pulses and the rising and the falling edges. And one thing we find is that actual signals are not going to be perfectly ideal like these perfectly square signals. You're going to have rise time, you're going to have fall time, and you're going to have ringing. So when we look at some of the signals back here in the lab on an oscilloscope, for example, when we do the RC time constant lab that we're going to work on, there's a little bit of a terminology and definition that we have to talk about. When we talk about rise time of a signal, what we mean is the amount of time it takes for a signal to get from 10% to 90% of its full value. And the reason we don't use 100% is because usually there's ringing, so it's hard to define where the top of the signal is. But we can just kind of average that and signal, say 90% and 10%. And a lot of times past the 90% point, you may have some weird things going on. So it's not always a nice signal to look at. So we define the rise time as being the 10% and the 90% points. I would just make a note in your notebook. And the fall time is the same deal. Wherever it crosses the 90% mark and the 10% mark, we would call this time here, we would call this time here the fall time, T fall. And normally we would call the 50% marks, we call it the pulse width. So whatever the 50% marks are, you go down, you make a line that goes down to your time scale, and then this would be considered your pulse width. Okay. And then to talk a little bit about waves, we talk about AC voltages. We have different waves in electronics. We have sine waves. We have, this represents an AC sine wave. Now if we DC level shift this sine wave, then we can get a DC sine wave. Notice that this sine wave has been shifted up so that the entire signal is positive. So there's no voltage below zero. And then if you continue to shift that sine wave, then actually it does not even touch zero. And then we also have square waves that go positive, they go minus, using the same sort of idea of having a switch to switch voltages high and low. We also have what we call triangle waves. These ramp up and they ramp down at a constant rate. They go positive and negative. And then we have, actually this is called a sawtooth wave. it ramps up at a constant rate and then falls almost instantly. We call that a sawtooth. And then we have complex sine waves. Sine waves that are made up of multiple sine waves. And then we have noise is random voltage, and you're going to always have noise. It's in the environment. It's in the that we can't get rid of. Noise by definition is noise that exists around us that is undesirable. It comes from arc welders, engines. It comes from other electronic inventions that we have, computers and things like that. And the noise that's in the environment, it usually adds to our signals, and then it makes the signal look like this. It looks like it's riding on top of it. You add the two together. And if you have a lot of noise, then your signal almost becomes indistinguishable. So now we want to get into what are the basic components of electronics. There's lots of different components. We've been in this electronics age for quite a while now, since the early 1800s. We've been playing around with inductors, coils, capacitors, and things like that. And so we have a lot of components to discuss. We have the most simple is wire and cable. Okay. So we have the wire is what carries the current. Okay, the wire is designed to be low resistance metal, like copper, for example, or it could be aluminum if you want to have a lightweight. But copper conducts better than aluminum, and silver better than anything. Gold has the least amount of contact resistance of anything. So a lot of terminals are made with gold, not because it's usually electroplated. And we have a solid wire. Solid wire has a single conductor, and then we have stranded wire. Stranded wire is twisted. Basically, it's twisted solid wire. Sometimes it's twisted multiple times. So, and the purpose of the stranding, there's actually at least two reasons why they do stranding. Number one, it makes the wire easier to bend. Okay, easier to bend. Anyone know of another reason why we use stranded wiring?
It's less likely to break from whenever it needs to be flexed. Well, a machine needs to move from a component that needs to have some flexibility in movement, like use stranded wire.
Yeah, that's another reason. What's another reason?
Conjunction of individual parts.
No,
Does it have anything to do with it?
probably not. Maybe on a very small level, but yeah.
Multiple connections at the other end.
Multiple connections? No, we don't do that. No, we usually when we have a stranded, it's all connected together. One of the original reasons why they used stranded wire was when they were running the transatlantic telegraph cable. It broke several times before it was successful. Actually, it took them many years to get that to work. But what they actually found is if you have a solid wire and it breaks, what happens?
You have an open and now you don't get any signal.
What happens if you have a stranded wire and one or two of them break? Do you have a connection?
Still good.
You still good because why?
Because you still have there's more wire.
Because that connection is shorted to the other connection.
Right.
So it doesn't affect the resistance that much. It's just going to have a small gap. Do you guys understand what I'm saying? That break in that one wire is still going to be touching the other wires. And so it's going to wrap around. There's going to be a small increase in resistance there, and it's going to continue to go.
Right.
It's not going to be a catastrophic effect. In fact, you could have multiple different strands broken along a wire, and it still work. And still work really good.
Right.
And you can take and stretch a small wire, and it won't break as bad as when you try to stretch a single wire.
Yeah, that's true too. For stretching, there's many reasons actually. The development of the wire actually was quite complicated, but
It's more forgiving than
Are we
It
gonna
is.
need to- Are we gonna need to remember them diameters?
No. But and some wires actually have they'll have some strain relief built into the cable or in the sheathing itself. But we do have what we call a AWG wire table, which we're going to work with. I'm going to give you guys a printout today, and we're going to work with that wire table. We have different gauge of wires. Okay, 16 down to well, you don't have these are. This is a small list, but you have double lot and triple lot and all these different gauges. But the gauging system is reversed in what most people would think. So the smaller the gauge, actually the larger the wire. Okay, and there's a certain diameter that matches up with that gauge, and there's a certain feet per ohm is the main thing that we're going to be looking at. Usually this is going to be specified in resistance per feet or 1,000 feet or kilometers. Okay, so it's going to give you a certain amount of ohms or resistance per 1,000 feet or kilometers, depending on what length unit you're using. Coaxial cables can carry high frequency signals. Always make sure you follow the rated current for the wire, because if you don't, then all wires heat up when you have current through them. Okay, that's just a given. And there's a certain amount of heat or delta heat that the wire is allowed to have in order to meet its specification. If it goes above that, then it could reduce the reliability of the wire. It could start to form voids in the wire, and especially in places in the wire that may be weak or smaller. Even contacts where you have the wire contacted are going to heat up more. So where the wire is smaller, it's going to heat up more than where the wire tends to be larger. So we want to make sure that we always follow the specifications on the wire sizes. And also, it's interesting to note that, for example, a speaker, which is a common load for many electronic components, a speaker is made with a coil of very fine wire, and the wire is so fine that after they wrap it around 100 times or so, it has a resistance of about 4 to 8 ohms is typical. And that comes because of the small diameter of the wire and the length of the wire. So the next component we're going to talk about are switches. The switches are used to permit or interrupt the flow of current. They're also used to direct current to different points. So the basic switch is just a knife switch. You can imagine having a copper or brass switch here, and when you push this lever down, it's going to close the circuit, and that would be called a single pole, single throw switch. And this would be a symbol. You'd have a circle with a pointed arrow, or sometimes you can eliminate the arrow altogether and have just a simple single pole, single throw switch. The acronym for that is SPST, single pole, single throw. You need to know what that is. You can see different ways to make. This shows the contact has been made. This shows that the connection has been broken. There's other types of switches. Okay, there's the single pole double throw. That means you can throw this voltage, if you have a voltage here, or current, you can throw that voltage or current in two different directions. Okay, for example, if I had this connected to 5 volts, I could have this, or let's say that I had this connected to 5 volts on this side, this to ground, then I could have this connection going to a microprocessor or a digital circuit, and I could connect in 5 or 0 volts. So So, or you could use it in reverse. You could connect the signal that you wanted to convey on this side and connect to 2 different points. So either way. And then you have a double pole single throw switch, which means you could have possibly a differential signal, maybe a plus and minus volt signal. And when you would throw the switch, these are mechanically connected, and that's what's indicated by this dotted line here. The dotted line indicates that there is a mechanical connection between the switches, so that when you move the lever, the toggle, whatever type of mechanical mechanism it has, then they're both going to move together. Okay? And then you have the double pole double throw switch, which has similar to the double pole single throw, except in this case, the double pole single throw, at one position the switch terminals are going nowhere, whereas over here then you always have a contact made. So in that case we call it a double pole and double throw switch. Okay. And of course there's different types of switches. We have push button, we have normally open, normally closed. This is a symbol for a normally open push button switch. They're normally spring loaded. And this is a push button for, or this is the electrical symbol for a normally closed push button switch. So when you would push down here, then the switch would open. Okay. And you also have rotary type switches that look like pots, but instead they rotate. So you would have a switch maybe that went like this, and you maybe have a terminal in the middle that goes out like this, and you have wires coming off of here, and you have an arrow here, and you could rotate this to different positions. Okay, so that's a rotary switch. We have different types of other types of switches, like the toggle switch, rocker. Most of these switches fall into the basic category of single pole, single throw, single pole, double throw, double pole, double throw, or double pole, single pole. So they may have, you may have a switch that looks a lot different than another switch, but they could actually have the same electrical function. So you could have 2 switches that are single pole, single throw that look completely different. So really this is, for example, a push button switch is really a single pole, single throw switch. And a rocker switch, depending on how many contactors it has, it could be any of these up here. You know, it just really depends on the configuration of the switch. You have to really, the best way to tell is to look at, see how many terminals this switch has on it. So if it has 2 terminals, that means it's a single pole, single throw. If it has 3, that means it's a single pole, double throw. If it has 4, a double pole, single throw. And if it has 6, then normally it's a double pole, double throw. That's the easiest way to determine. For example, on the back of a switch, if it was a double pole, double throw, normally it would look like this. Like for a slide type switch. That's what it would look like on the back of it. And it would have little holes here for you to put your wires in. And normally, almost in all cases, what that means is these 2 terminals in the middle would be your common double poles. And then this would be one throw position. One throw position, and the other ones would be the other throw position. Okay? As opposed to a single pole double throw, it would look normally like this. So you'd have 3. And of course, the double pole single throw would have 4. So that's normally the way it works. Alright. Okay. Relays. Okay, so if we combine this whole idea of electromagnet with a switch, then we wind up with what we call a relay. Now, a relay is an electromagnetic switch, and all of these devices, anything that has mechanical action and electrical properties, we usually call electromagnetic component. Okay? Or, I'm sorry, electromechanical. Electromechanical. So a switch is electromechanical because it has mechanical properties and electrical properties. A relay is electromechanical. A potentiometer, a rotary switch, those are what we call electromechanical. Okay? And a relay is basically an electromagnet combined with a switch, a small current flowing through a coil of wire. Now, the coil of wire is normally small wire wrapped around many times so that, according to the AWG wire table, the switch, if you can calculate the resistance. So it's normally designed to have a fairly high resistance. For example, 50 ohms would be common. 50 ohms so that it would not consume a lot of current. Okay? Because the idea is you want to use a small current to control a much larger current. So in order to do that, the requirement really is that the coil that you has a does not consume too much current. Otherwise, you would defeat the purpose. So a small current flowing through a coil in the relay creates a magnetic field that pulls one switch contact against or away from another. Joseph Henry, an American, invented the relay. And Samuel Morse went to him and said, "Hey, I've got an idea." Actually, Samuel Morse went to him, and Henry said, "Hey, use my new invention." And that's how it became so popular. The secret to the Morse code was the relay, because the relay allowed you to pump up the signal from each station. Because you have a battery at each station with a relay, and it would basically re-amplify and send the signal out. Because it used this, they would each have their own new battery. So, the symbol, the schematic symbol. Now, I want to reiterate the fact that I would like you guys to be taking notes, and you're going to see all these concepts on a test and in labs, and so you really need to make sure you get these concepts and these symbols and their operation. You understand them. So the relay symbol and the arrangement can have single pole, single throw. From now on, I'm just going to be I'll just use the acronym SP, ST, SP, DT, DP, ST, and DP, DT. So you can have a relay that has, normally those are the most common. Of course, you can have more. You can have a switch that had quad poles and quad throws, but but I'm just giving the most common ones. So in this case, we have a switch that has, what type of a pole and throw is this switch for this relay? Single pole, double throw. So throwing it in two different directions. What do you think this little wire and this rectangle indicates? What is it trying to indicate? Electromagnet. A coil of wire around a magnetic material. Could be ferrite, could be, usually it's iron. Steel. Usually it's steel. Could be iron, but usually steel. Okay, that's pretty much it. We also have reed switches. Reed switch is you put a magnet close to this switch, and the magnetic field causes the contacts to magnetize, and they'll actually connect together. It's a single pole, single throw switch. These are used. These are used used to be used a lot for security systems. But today they use more electronic components, like Hall effect sensors and things like that. But yeah, I don't really know how common these are today, but I know they they were used. Today they've been replaced a lot probably by Hall effect sensors and things like that. Yeah. The Hall effect is actually effect of a semiconductor material when you put a magnet in front of it because of the magnetic forces that we talked about, the magnetic rotations. It'll actually cause it'll cause the electrons to shift on one side of the semiconductor material, which will cause a potential difference across the semiconductor, and you can measure that and amplify it, and so that's more of a solid state. It's kind of like a solid state reed switch.
Those types of switches are also used a lot for fire alarm systems.
Yeah.
For doors and stuff that
Yeah.
are open.
Yeah.
They
Mm-hmm.
create a magnetic field, and whenever the fire alarm goes off, the magnetic field stops.
Yeah.
The doors close.
You could use it as a proximity sensor in industry, but I don't know. I don't know what they use. I mean, they have proximity sensors. I don't know what's inside of them. You could have different technologies inside of these sensors, depending on what they determine would be the most robust and reliable.
They used to be used a lot for logic before they went to solid state.
Logic.
Switch fast and
Mm. Yeah, they used to actually use, kind of interesting, they used to use these little ferrite beads for logic to store memory, because once you magnetize it, it retains its magnetism, so they would actually sense that. But
How long ago was that?
long time ago,
50s?
a long time ago, you actually see boards with little
I've
ferrites.
worked on it before, so it wasn't that long ago.
Yeah, because when you magnetize something, it retains its magnetism. And there's a hysteresis effect that occurs, which so they would use that for memory. Well, we also have moving coil meters. Okay, and I'm actually going to give you a little bit of a lab on this as well. And here's an example of one that we're going to use in the lab. It has electromagnet inside of it and a little spring. But a coil on a pivot between the poles of a U-shaped magnet will rotate when the currents pass through the coil. And we can use these as in their most fundamental use. They measure current, or actually they're measuring magnetic field, indirectly measuring current. But you can also configure these to measure voltage, and we'll do a lab to show you how to do that. Basically, they measure a current and they have a scale for a current, but you can put a resistor in series, and if you select the right by scaling the resistor, you can actually make a voltmeter out of it by using Ohm's law. Pretty simple and neat thing to do. So microphones and speakers is also another important component that we use a lot in electronics. A lot of times we will call these transducers. Anything that picks up noise or vibrations or things like that, we would call a transducer. Something that generates a voltage based on mechanical movement, I guess you could say, would be a transducer. But these are forms of transducers. And a microphone converts sound wave vibrations into corresponding electrical currents, and there's different ways in which they do that. So the back and forth movements of a small flexible film or foil called a diaphragm. So really, what you do is you take a piece of paper or something we call a diaphragm. It's anything that is coupled to the surrounding air, because when the air moves, we want to couple that to the air and cause it to vibrate. And then we call that the diaphragm. Then we try to attach something like a coil of wire or in close proximity to a magnet in the most basic form to capture that movement to induce a voltage through Faraday's law and then create an electrical current. But there's also different ways to do that. The first method of doing that was Alexander Graham Bell actually took a electromagnet, and very similar to the guitar pickup that I demonstrated to you guys, Alexander Graham Bell took a small, thin piece of metal, I don't know what the composition of the metal was, in close proximity to an electromagnet, and he would speak into that small little sheet of metal, and it would vibrate, and just like the guitar pickup, it would produce, those vibrations were the representing the voice. So that's how he did that. And then Thomas Edison came along almost immediately, and the problem with that was it was hard to vibrate that piece of metal. It had mass. So Thomas Edison came along and invented the carbon button, which was much a huge improvement. But still, of course, Graham Bell got the invention for the telephone. But the carbon is the black stuff left after you burn a fire. Mm-hmm. Carbon is what's in your engine. Carbon has electrical properties. It's conductive. And so if you take carbon, it's also in your pencil lead in the form of graphite. If you take carbon and you move it, put pressure across it, then it changes its resistivity, and you can use that, make a carbon structure out of paper or whatever, and use that, measure that resistance, and then convert that to voltage. Dynamic is a small coil through a magnetic field. That's the professional microphones that we use today. The professional ones, they are usually dynamic. Condenser is a moving diaphragm, alters the distance between two metal plates. The result is a proportional change in the capacitance. That's a condenser type microphone. And then we have a crystal, is a piezoelectric. That we have some of those back in the lab, but it's basically just a crystal, and a small thin one. And when you bend a crystal, it produces voltage across it. It's called the piezoelectric effect. And then you can amplify those and have a microphone. Also, you can use a speaker. Actually, you can take a speaker and talk into it, and it will produce a voltage. So you can use a speaker as a microphone. Okay. In fact, you can take one speaker, connect to another speaker, string it across the room, and talk into it, and the other person will be able to hear you on the other end. That's basically Alexander Graham Bell's invention. That's what it was, with no amplification. Okay.
And vice versa, Mr. Ofsted. We'll work the other way also, I guess.
Yep, works both ways. And we have here a speaker. Of course, the speaker is just an electromagnet attached to a paper cone, and then there's a big permanent magnet. And so when you put current through the electromagnet that's connected to the cone, it produces a magnetic field that either attracts or opposes the permanent magnet. So it's going to cause the coil to move. That coil moving varies the sound pressure around it, and sound pressure by definition is, it creates a pressure variation in the air or the atmosphere around it, and that by definition is sound. Sound is simply just variations in sound pressure. Now we go to our final component for today, and that is resistors. Resistors come in different shapes and sizes, and they all do the same thing. They limit current. We've talked a lot about carbon, and we're going to talk about carbon again, because resistors, the most common resistor are carbon resistors. Okay? So they got carbon inside there, and the different composition of the carbon, different amounts, whatever, the different shape, can make a different value of resistor. And what happens is the current coming in, this shows here the current cannot flow as easily, the electrons get dispersed, and so the current flows down. So you have less electrons coming out than you do have coming in. So it has a protective housing. It has a wire lead. You also have surface mount devices today. You have color bands on here. These color bands indicate the value of the resistor. Or with the surface mount resistors, they are usually marked with text. And yeah. Resistance can be changed from one resistor to the next by simply changing the ratio of carbon particles to binder. So that's how they make it. It's a carbon mixed with a glue-like binder. And you can make a do-it-yourself resistor by just drawing a line on a piece of paper with your soft graphite pencil. Used to be lead. It's not lead anymore. It's graphite. But graphite is carbon. So lead wouldn't really work. Lead conducts, so lead would work too. The resistance of a single line may be too high to measure, but the thicker you draw it, the lower the resistance. The thinner you draw it, the higher the resistance is going to be. The color code that's on the resistor has 3 bands, and usually has actually 4 bands, which is a tolerance band. We have the first one. So what is the code? The code is the first one is the most significant bit, and then the second one is in the second position, and then you have a third position that's the multiplier. So the way it works is you assign a color. The way I think about this is I remember Roy G. Biv.
Right.
Roy G. Biv. You have a question? Go ahead and ask your question.
Are we going to get a copy of this?
Yeah, it's on Moodle. The way I remember this is I say Roy G. Biv, and I get most of the table. Most. Now, the only thing you have to remember then at that point is you're going to have to add black brown onto the beginning and gray white on the end. And that's pretty easy to remember because black is the darkest color. White is these are opposites of each other. So remember that black is 0, white is 9, and of course, brown is very closely related to black, and then gray to white.
Take out the indigo.
Yeah. So Roy G. Biv. It's like Biv. Yeah, it's not I. BV.
Yeah, a lot nicer than what I was talking.
Yeah, there's non-nice ways to do this, but I'm not going to say what that is. And okay, so what does a multiplier mean? The third number does not represent a specific number, but more of a multiplier. That means how many zeros do you add to that? So, for example, most common resistor is brown, black, red. Brown is 1, black is 0, red is 100. So that means 1 0 times 100. Or in other words, with 2 zeros on the end. So 1 0 0 0. What would that give you?
1K.
1K. So brown, black, red is the most common resistor. That's why we only have 2 of them in the bin back there, because everyone wants a 1K resistor. Every lab says, use a 1K resistor. Okay, use a 1.2K resistor instead of 1K. And then the third band is normally going to be, like gold would be 5%, silver 10%, none would be 20%. So the thing about resistors, guys, is it doesn't really have to be perfect. Anything within actually 100% usually will work. So if you got a 1K resistor, usually 2K will work. But, if you got a 1K resistor, use 1.2, use 1.3, use 1.7, use whatever use something that's close. It doesn't have to be, unless we're, in most situations you can substitute with one that's 20, 30, 50% variance. And normally when let's say you use Ohm's law and you calculate a resistor, it's never going to be exactly matched. So we have these standard resistors. So we don't have bins back there that have every single possible combination that you could put in your calculator. or the, so just pick something that's as close. Normally you're going to calculate a value that's in between two standard values, and what you need to do is, so you may calculate a value that's right here. Okay, and then there may be a 1K here and a 1.2K here. And you may calculate 1.15K. Well, the closest thing would be to just use a 1.2K. Because the reason I say this is because I get a lot of people come to me and say, I can't find a 1.15K resistor. Can I use, what do I do? Or, just use the next closest one. It's not that big of a deal. It's not the end of the world. So, yeah. Question?
Go up in value, don't go down in value very much. But it
Yeah.
increases your current flow.
Yeah.
So the next step up, they're stepping down. Yeah.
Substituting resistors. Now, one thing I will say about resistors is don't always trust what's in the bin, because people do put them back wrong, just like in the libraries. People put them back wrong in the wrong spot. What else should I say about that? We already talked about substituting. You can also build custom resistors by adding them in series or parallel. And sometimes you may need to do that if you don't have the exact resistor you need. Then you may have to add some in series to get it. But normally, you can just substitute one that's close, within, 20%, 50% even, most of the time. Now, resistors do have ratings. Those ones back there are rated for 1/4 watt. Now you have 1/2 watt, you have 1 watt, you have 5 watt, and the larger wattage ones are going to be ceramic, and they are going to look. They're going to look like white pieces of ceramic box shaped things like this. Okay. Then you have 1 watt, and you're going to have 5 watt resistors, and even higher wattage. But we have some larger wattage ones back there. Those are to the left, to the far left. We have some higher wattage ones. So typically we will have a 1/4 watt is the most common. We may have some 1/2 watt back there. It depends on the size. Now when we do the lab, I'll do a quick little demo and show you which ones are what. Okay. I don't really have any good pictures of the wattage here. Some resistor shorthand. You'll often see resistors with a K or an M. A K means 1,000, which means kilo, for the Greek word 1,000. Okay, so I didn't actually know that, but kilo is Greek for 1,000, and then therefore 47K means 47 times 1,000, or 47 with 3 zeros after it. M is shorthand for mega, and mega means 1,000,000, so 6 zeros. So there's different types of resistors. Carbon is the most common, but we also have metal film. Various kinds of resistors use a thin film of metal or a metal particle mixture to achieve various resistances. We already talked about carbon. Wire-wound resistors. Some resistors use a very thin coil of wire. They can be very accurate and can have a lot of heat. Photoresistors, also called photocells, made from a light-sensitive material like a cadmium sulfate, increase the light level, decreases the resistance. So we have these little resistors, light-sensitive resistors back there. And actually these are used sometimes on landscape lighting to tell your lights to turn on. So yeah, they're actually popular for that.
What's the symbol for photoresistor?
And we have a thermistor, I'll show you in a minute, is a temperature-sensitive resistor. Increasing the temperature decreases the resistance in most cases. And we have variable resistors. It's often necessary to change the resistance of a resistor. Variable resistors are called potentiometers. Potentiometers, or variable resistor. These confuse students a lot. So we're going to do a little lab with these today. They can be used, many times these are the volume knobs on your radio in your car, or the dial for anything, for a lot of different things. And sometimes we have variable resistors inside of your components that are only used during manufacturing to adjust parameters, and those are called trimmers. And they are smaller, and I will do a lab demo to show you what a trimmer is, because I don't have a picture right here. But it's just a smaller version of a potentiometer, and it has a little tab in the middle of it that rotates, and it usually has a little slot for a screwdriver where you can adjust that by twisting it and turning it. So, what are the symbols for resistor? The symbol for a resistor is a straight line, and then you make like a sawtooth pattern. Okay? Now for a potentiometer, you have the same sawtooth pattern with a arrow in the middle, which represents the wiper. Okay, this is called the wiper. Okay? It's just a potentiometer variable resistor is just, you can actually use it just like a resistor. If you decide not to use the wiper, you can just use it like a resistor. As a rating, just like resistor. Usually it's a 5K, 10K, 20K, 50K, or 100K. A thermistor has a sawtooth shape with a T in it and a circle around it. A photoresistor has a little lambda symbol in the middle of it to represent photon. It has arrows pointing into it. And it has a circle around it. Okay?
What's that symbol called? Inside there?
This is lambda.
Lambda.
That's a Greek lambda. I've noticed that all the photosensitive elements have this lambda inside of them, like a solar cell. I don't think LED doesn't, but okay. The class is actually over, but I'm just going to go over really quickly, and you guys can look at these on your slides. Write this in your notebook. Resistor combinations. If anyone needs to go to class, you can go ahead and leave right now. But if not, just about three or four more minutes. We can combine resistors in series, and the equation for that total resistance is R1 plus R2. So the total resistance here seen between these two terminals is going to be R1 plus R2. You can also put resistors in parallel. The total resistance across the two resistors in parallel is going to be R1 times R2 over R1 plus R2. Okay? I would write that down and memorize it. If you have more than 3 in parallel, it's a little bit easier to use R total equals 1 over R1 plus 1 over R2 plus 1 over R3, etc. And the final thing to talk about, the basic voltage divider. It says super important. Super important. V out here is determined by the ratio of R1 and R2. Here's the formula. Okay, if we say that this is ground, so this is our reference point here, then we would say that V out is going to be the resistor on the bottom, R2. It's the resistor between what you're calling V out and ground, really. Okay? So since we're calling this V out, and we're calling this ground, then we say the resistor that's in between those two reference points is R2. So that one goes on top. Okay? So R2 goes on top. Then you just simply add both resistors. And you have to multiply that times the battery that you've connected to. Because really, R2 over R1 plus R2 is just a ratio. It's a dimensionless ratio. So you're going to get something here that's like 0.5, for example. It's not going to have a dimension. So you have to multiply it times a voltage to get a voltage out. So if R1 and R2 are equal, what are we going to get out? Let's say that Vn is 1.5 volts. And let's say R2 and R1 are the same. What are we going to get for V out?
Half the voltage. That's
Yeah.
the input voltage.
Half the input. Which is what?
0.75.
0.75. Yep. And that's it. And there's going to be a tutoring session today for those interested. And then we're going to meet back here at 1 o'clock for the lab. Thank you.